Wow. Good morning, and thank you for being here. So, as you heard from my introduction, I'm quite passionate about serverless. I really think it's showing the direction where software development is going. But we've been unfair. I think we've been unfair because we talk a lot about functions, services, methodologies, but we don't talk enough about events. And I think events are really important in building serverless architectures and serverless applications. So this is my opportunity to make up for that. So why events are important? Events are important, the reason is because how serverless applications are built. And if we look into how we build serverless application, on one side we have fully managed services, like storage, databases, or an API gateway. And some of these services have been there for a very long time, like Amazon S3 was launched 13 years ago, but we never said that it was serverless at the time, and we didn't say that it was storageless at the time. It's when we start to use functions. So we launched, for example, Lambda, AWS Lambda at the end of 2014, and then we start to see the term serverless pick up and be used. Because with functions, we can put our own business logic, our own unique problems into the code. But how do the function and the fully managed services that provide the storage, the database, the interface work? They talk using events. So you upload a picture as a customer, you update a database, you insert an order. This fires an event that can trigger the execution of your business logic inside a function. And then the function can eventually access other services, so maybe update a database, and this fires another event. So this flow of events, firing function, doing something, and accessing other services is really at the core of creating really interesting serverless architectures. But what is an event? Well, if you look into the dictionary, an event is something that happens. But what is really interesting is that events tell us a fact. So a file has been uploaded, a database item has been updated. So this is a fact. And it's also an immutable fact, because when something happened in the past, it's never changed. I can update a database again, but the fact that the database was updated or that the file was uploaded, it will always be true. And immutable artifacts are really important in distributed architecture, because in a distributed architecture, when you see some data, you never know if someone else has updated this data. But if you receive an immutable fact, you know that that's true. Maybe something else happened after that event, but up to that event, that's the source of truth. And actually, it's really a time series. If you look at the events, you normally have a timestamp that tells, hey, at this moment in time, this happened. A customer has been created, an order has been processed, or a payment was successful. So it's really an immutable time series of facts about our business. And actually, this is Greg Young, probably the inventor of CQRS, and we'll come back to that afterwards. When in this presentation, he was explaining that this immutable time series is really making me aware that there is time in our application. Because normally, when we used to develop our application on a single server with a relational database state in, we assume that everything happens instantaneously. But this is not true in a distributed architecture. You have to consider space, we have multiple servers, and time that is introducing latency. So this is two concepts that we have to actively use when we develop and design our architecture. It's part of the system that we're building. And the idea is really that with events, we can switch when we design our application from trying to analyze the current status of my business to thinking on what is happening in my business. So, for example, when we use a traditional approach and we want to model, for example, a warehouse, what happens is that I have my rules. So this is my parcels, this is my warehouse. A parcel must be in my inventory table, and then if I scan it, I can ship it away. I'm really giving orders, commands like create user, ship parcel, and the language is direct, is different from events. Events tell me what is happening. So maybe a user has been created, a parcel has been shipped. And also the way I can model business is different, because if I scan a parcel and there is an error, this parcel is not in the inventory table, what should I do? Should I stop the business of my company until someone is inserting a new record in the inventory table. Maybe I ship it and then annotate that this event happened, and then I can process it afterwards without blocking my business. So it's different. It's also creating autonomy, because my service is not receiving commands, but is listening for facts to happen. And this is one of the distinctions that is very common in programming between commands and events. So when you give a command, the language is different, as I was saying before. An API, normally you create a user, you add a product. An event tells you what happened. No? A user has been created, a product has been added. So commands has an intent. I tell you what you have to do. It's a one-to-one communication between someone and a service that is receiving this command. Events are for others to observe. So I'm telling everybody, hey, a user has been created. So if I tell Alex, hey, add a user to the database, he will run and add the user probably. But if I tell you, hey, a user has been created, maybe more than one people here is interested and takes this information and does something with this information. So it's much more reusable, and you create autonomy inside your architecture. It's not one-to-one, it's one-to-many. And in the same presentation, Greg Young was telling us this is really changing the way you think about the system that you're modeling in your application. No? You're changing from structure to behavior. And the behavior can be different from the model that you create. So you can also use this to learn about the model that you're building. Because sometimes when you design the model of your application, you assume something that is wrong. If you listen to the behavior, you can learn that. If you enforce it, you just force the people using your application to do what you think was correct, and maybe it wasn't. So what can a function do with events? So a function can react to these facts and do something that is unique to your business logic. So the events are flowing in, the function takes these events, if it's interested, can do something, and can call other services, like maybe update a database or store some information somewhere. And these events maybe come from another service. So this is starting to create a chain of events that from one service go through your code and then through other services that can fire other events that are for others to observe. And a slightly different distinction is probably if this function is using a private database, a private storage. This is still another service, but this is more private to the function. So it's something that starts to encapsulate some logic, your logic with your data. So this database should be private. You shouldn't have this database shared with too many functions. So probably having 2, 3 functions together sharing a private database is correct, and it's what we normally would call a microservice. I don't think that a function is a microservice. A function is a functionality of a microservice. Probably 50 function is too big as a microservice, but it really depends on what you're building. So and in this way, we are building microservices that replace the traditional API-driven command approach of do this to an approach that is more based on events. So if this happens, then do this. So for example, you can have an API gateway that gives as an API that tells, hey, create a user request. So this is, in this case, a command. This goes to the different function inside your microservice. In this case, create a customer. It will update the local database and then can publish this information, for example, using a publish and subscribe mechanism like Amazon SNS to a topic, say, hey, a user has been created who is interested, can do something with this information. And actually, you can also call functions, for example, Lambda directly. Lambda is a native HTTP interface, is the interface that you use with the AWS SDK. And I would suggest that you look into this interface because it's very powerful, and sometimes you don't need to put something in front of a function to be the entry point, the boundary of your microservice. Because the Lambda invoke allows you to call the function synchronously and asynchronously. So that's already an advantage compared to traditional APIs. And also implements AAA, so you get the authentication. You use the traditional AWS signature for the API. So it's the fact that this signature version 4 tells you that it's not easy to build a signature in the first attempt. So at AWS, it took us 4 attempts to arrive to this level of security. And then you get the authorization using the roles. And then you get the accounting. You can go on CloudTrail, for example, and enable accounting on the execution of functions to know if, for example, a function that is under compliance is being executed or not. And even better, instead of using SNS or a messaging system, you can just fire an event from your database. So for example, if you use DynamoDB, you can fire an event and say, hey, a user has been created straight from the database as the event generator. So this looks nice. I can build my microservices. But what about integration? Now, integration is where things get complicated, especially with microservices. So let's take this super simple example. Now, I create an order, and to ship, maybe it's a physical item, I need to reserve this item from my warehouse, and then check the payment, and then ship it to my customer. Looks super simple, but there's something here that in the past I would put into a single transaction, because I only want to reserve an item if the payment is successful. Otherwise, I don't want to block an item from my warehouse. So I coordinate two microservices, two functions in an easy way. So as I said before, the data should be local to the service. So we should definitely avoid any interconnection between one service looking into the database of another service, because then we create this classic distributed monolith that is just more complex to build than a traditional monolith. So data should be private with the microservice. This creates complications, but it also has its good side, because this is what normally is called polyglot persistence. So each microservice can use a different database. So you can choose to use relational if it makes sense, but you can go NoSQL, you can build a graph model of your data, you can store a time series, or you can have a cryptographically signed ledger that tells how data is evolving in your database. So there are pros in this approach of private data in microservices. The problem is, and this is the mandatory slide with the cap theorem in this kind of discussion, is that it's impossible to build a distributed architecture where I get, at the same time, consistency, partition tolerance, and availability. And let's dive a little bit deeper than usual into this. So let's say this is my distributed system. This is not necessarily a serverless system. It's just 3 partitions with some data that is stored and replicated across partitions. So if I want partition tolerance, that means that if a node fails, or even if the whole connection, all the network connection between 2 partitions fail, then my data is still preserved somewhere. I can tolerate this, and I can move on. So this is interesting, but it's not telling us that I don't lose data here. That's for another of the 3 letters of the theorem. Availability tells us that I want my system to be available for my customers. So if I get some data out of this system, I need to be able to extract information and get data. Maybe it's not always the correct information, but I want to do that. Consistency is telling us that if I get data out of this database, I only want to get the latest version of the data. So for example, if I have version 3 of my item, I don't want to get version 2 from one of the partitions. I want to get the latest version from all the partitions. So this is something that apparently is quite useful. Problem is that if you try to build a model on top of these 3 features, it's impossible to have all 3 at the same time. So we need partition tolerance because we need to protect our data. We can't lose the data of our customers. We need availability because we want to serve our customers most of the time. We don't want to fail and close our application often. So this theorem is telling that we can't have at all time all 3 available. So normally you can have, but not at all time. So we have to compromise on consistency. So that means the implication for a distributed systems like the one that we were saying before is that 2-phase commits or distributed transactions are not just complex, are almost impossible to build. It's just something that we just say, no thanks, we don't want to do that. So we have to welcome eventual consistency so that we don't have the full strong consistency that we would like to have, and we have to implement idempotency. So this is not a new concept. So this is an article from Werner Vogels, the Amazon CTO from 2008. He was explaining how we are building systems inside Amazon. And the idea that we have is that we can't have consistency together with availability and partition tolerance. So we have to compromise on consistency. So we want to build a storage system that guarantees that an update, at some point in time, all updates will reach and will be returned as the last value, but we don't know how much time it will take. We will take time for the data to propagate in our systems. So let's go back to integration. We can't do a two-phase commit or a distributed transaction here. So how can we solve this? Actually, there have been in the past lots of attempts to solve this kind of problems. One interesting one is from 1987, I think, and it's the idea of sagas. So at the time, the idea of distributed database was probably not in the mindset of many people. But still, with a single database, they were having the problem of long transactions. So if you have a single database and you have a transaction lasting minutes or hours, this would block, with a traditional relational model, all the other access to the database. For example, if you produce a report, at the time, you were running the report on the production database. The idea of having a read replica in 1987, maybe on an ephemeral hardware, would just be considered a crazy idea and not something that you could implement. So on the production database, I run my reports, I block the database for 15 minutes. This is not good. So how can I solve it? So this idea of sagas is that, OK, let's take our long transaction, and let's split it into sub-transactions. I don't need to do everything at once. I do it in steps. And this is not bad. I can do my first part of the transaction, maybe and then the second part, the third part, and the fourth part. But what happens is the first part goes on, and then my second step, my second sub-transaction fails. Well, I need to create what is called a compensating transaction. I need to manually roll back what the first transaction did to revert it on my database. So it's not so nice. And again, if it fails the second or the third step, still I need to write compensating transaction for all the steps. The only step that doesn't need a compensating transaction is the last one, because if the last one is successful, I don't need to roll back by definition because I completed my whole list of transactions. So one, at least, we don't have to do it. So let's go back here. We can do a saga transaction. We have two steps here. So we apply the same concept not to a single database, but to different data structures. First, I reserve the item, and then I manage the process payment. And I need, since I have two steps, I need one compensating transaction. So if the payment fails, I need to unreserve the item and roll back the first step. So it's not that complex. It's doable. And this works very well also with events. So I created the order, the new order is passed to the reservation system that passes the information that the item has been reserved to the payment process. And then if the payment is confirmed, I start the delivery. If the process payment has some errors, and this is where I didn't put an event, because any kind of error, it can also be an infrastructure error. It happens with serverless as well. But any kind of error is something that I need to catch. So that's why we have in serverless the idea of dead letter queues. So if this function really has errors, it's impossible after maybe 2 or 3 attempts to complete this payment, I get a dead letter queue that takes this event, and this is passed to the compensating transaction that will unreserve the item and clean the status and maybe cancel my order or maybe send an email to the customer. So this is not bad. And this idea is actually something that I took from a more recent article on sagas that is from just a few years ago, that is distributed sagas. So applying sagas to distributed architecture like the one that I was showing before. And an interesting concept here is that, of course, the important role for running these sub-transactions and this compensating transaction is who is coordinating the work on all these high-level transaction and compensating transaction. And there are, as usual in programming, 2 different approaches. The one that we saw is the idea of choreography, so an event-driven architecture. There is no central structure. Events will allow this transaction and compensating transaction to work. But on the other way, I can choose orchestration and commands. And the idea here is, for example, to design a process like this that will define exactly what I have to do and how to roll back if something bad happens. And if we look at this, it's just a graph. And it's, if you studied computer science, this is a state machine. And it's a state machine, so that means that, for example, on AWS, you can implement this in a step function. So another approach to do distributed sagas is to create a state machine that has the steps with the transaction and the compensating transaction. And this also allows you to manage retries in a much better way, because you can decide to retry 3 times the reservation, or maybe more times the process payment, because that's usually provided by an external company that you can manage. So if they are slow, you don't know what is happening, maybe. So what can we do better here? we still are doing lots of updates in our database. And I also like this is very old. It's from 1981. Jean Grey used to work for Tandem Computers, these very big fault-tolerant machines that were sold in the 80s and in the 90s. I still remember that because they were used, for example, in the first generation of the prepaid mobile phone systems. So they were built using this tandem computer because the prepaid system of a mobile phone couldn't fail. Has anyone here ever played with tandem systems in the past? Just to know how old I am? Oh, good, okay. So the idea is that he was reflecting in this article on the idea of transactions. And he said, actually, we have a few hundreds of years of history of transactions. We were doing transactions on books. And normally, we never do updates in place. You never do accounting. I think it's forbidden in the law of most countries to cancel something and just replace. You just append stuff one after the other. And then you can add everything up and understand what is happening. So can we bring this idea also in the space of events? Well, it fits actually very well, and it's the idea of an event store. So I store all my events together, and then I can try to understand how I can use this event store to give information to my business. And this is an example of a model that works very well with normal NoSQL databases, because I have my timestamp, then I have the actor who is being affected by this event. It's a customer, it's an order, it's a payment process, and what is happening with this actor. And this works very well because if you have a NoSQL database like DynamoDB, you can use the who as a partition key of the database, and then you can use the time as a range key, and then you can say, let's fix the who, like customer 1, 2, 3, and let's see sorted by range key, everything that happened for this customer, and you can relatively easily, because a customer will not have millions of events, rebuild the story of your customer and understand what is happening. So this is not bad. So we can build what is normally called an event sourcing architecture, where you get your initial commands. So you, for example, create an order. This create order is translated into an event, is written into my event store. But then if I want to get the status of my order, where can I read it? It's not easy. As I said, you need to manipulate the data. So normally what you need to build is a projection. So take all your events and project that information into an updated data store that tells you what's the status of your orders, for example, in this moment in time. And this works very well with this approach where we separate the commands and the queries. And this is the CQRS that I was mentioning before. It's the idea of segregating the responsibility of who is reading from your commands, your API, your main public interface, and who is writing into that interface. And this works very well at microservice level. So each microservice can implement this kind of differentiated architecture. And now the event store can fire the functions as before. So I store, for example, on a database like DynamoDB, the event, this trigger an event, and this is catched by the reserve item because I'm creating an order. So first I reserve the item, then I process the payment, then I start the order delivery. And if something bad happens, I can cancel the order. And the additional benefit of event sourcing is that it's append only. So I'm not overriding like I would normally do the order in the database, but I append another information. This undoing the previous step, saying, hey, this order has been canceled. If I build a new projection of this order, this that was happening before is not valid anymore. So it's probably easier to build, and you don't need to update. If there's errors, you can always have this auditing log of everything that happens. It can help you rebuild what is happening. And you can also rerun events. So in this architecture, if you store the events from the production system, you can rerun the events in your test environment and easily test what is happening in an environment that is very similar to what would happen in production. So how can we simplify event processing? So I really like this architecture. And if you look into software architecture presentation in the last 10 years, normally there's this history of culmination that ends with, OK, event sourcing will solve all our problems, and that's where we want to do. But then very few people implement that, especially if you don't have a very complex problem. So how can we make this easier? So let's do, so we're here because we're interested in serverless. So if something is complex to manage, we expect someone else to make it easier. So as AWS, we're reflecting how can we make this easier, no? And actually, the whole idea is broader than this. So when you build a serverless application, can we make it easier to solve recurring problems? So let's take this example from a completely different domain. And it's the example of monitoring social media. So most of our customers tell us, I want to monitor social media, for example, Twitter, to see if someone is speaking about my products, my brand, so that I can act on that. And this is super easy to build with serverless. Now you use to like CloudWatch events that every minute, every 5 minutes, fires a function that is calling the Twitter API. The Twitter API, you search for your brand, and you normally get a checkpoint that tells how far in the time you are searching, and then you can store the checkpoint in a DynamoDB table that will contain just one item. And then after 5 minutes, you take this checkpoint and say, hey, is anything happened after this checkpoint? And you get the new checkpoint and the new data. And then you pass the result of this search to a Twitter processor function that will act on your function. And this is where every customer has a different idea. So some customer, they just want to take the tweets that talk about their products, store them, and then they want to run analytics to see how people is talking about that. Other customer, they want to run, for example, real-time sentiment analysis, and if the tweet about them is negative, they pass the tweet to the customer support that will act on that tweet and maybe reach to the customer to say, hey, I can help, or maybe I can do something. So we have a standard component that most of our customers would have to build, and we have some custom business logic that every customer wants to do slightly different. So to solve this, we introduced the concept at the end of last year of nested serverless applications. And the idea is that inside an application, this is an example of a AWS SAM template, you can say inside my application, plug in this other application that will do the Twitter search. And in case I find something, this is the function you should call. This is my function that will process those tweets and do whatever I want. And this is the text that you need to search. For example, serverless or ServerlessDays if you want to trace the tweets of this conference. So in this way, I really don't have to write one line of code if not from my custom business logic. So this is something interesting because the idea of composing serverless application brings the simplicity to another level. It's not easy to think about that because we saw that there's lots of mindset that we need to adapt. So this is another step, probably a huge step to do. And we try to do the same for event processing. So this is what we call the event fork pipelines, and it's similar to before. So you have, for example, an SNS topic that it's a publish and subtract topic where you publish all the commands that you receive from your front end. So create an order, do something, and you publish this as an event, and then you process this event with your own custom business logic. This is something where we can give you tools, but we can do much more than that. And then we can create startup components, and that's what we did. We did for the things that are recurrent. So we created a pipeline that can store and backup all your events so that you can use them and maybe search easily. We can create a platform specific for analytics where you can get trends about the events and what is happening. And another pipeline that will help you replay those events. For example, in production, you solve a bug, and then you want to replay all the events that were affected by this bug so that you fix the database, or you want to replay the events in another environment to see in your integration environment how the production I/O would work. And this is an example of how we build them. So this is the event storage and backup. So we create a queue that fan out all the events that arrive on the input topic. Then we have a Lambda function that is just calling Kinesis data firehose. It's the part of Kinesis that stores events, stores data in this case, into different targets. In this case, we store on S3. And the nice part is we're not storing each event as a single object on S3. That would be completely unmanageable. But Kinesis firehose will automatically create a hierarchical structure of directories based on the date. And then you can then we aggregate those events by size and time. So for example, until you reach 100 megabyte or 15 minutes have passed, group those events, and then you store a single large file that is much more manageable than having all small files to process. And this is interesting, and the directory structure that we create is very simple by year and months. If you are into tools like Presto or Athena, So Presto is an open source tool from Facebook, and Athena is a tool that we developed on top of that. And the idea is that you need directories with a slightly different syntax. So I'm talking about Hive partitions for people that are into big data. So there's a tweak to do that. So instead of storing the date like year, month, and day, you store the name of the directory becomes year equal the year, 2019, month equal June, and this is the syntax that Hive and Athena and Presto expects to use this as partitions. So look for this tool, and if you didn't understand 100% what I'm saying now, consider that if you will find problem integrating this with Athena, there's a solution. And the second pipeline is to search for search and analytics. It's the same. There's all the events go in a queue. The Lambda function is using Kinesis data firehose, this time to write on an Elasticsearch service. So if we enter into serverlessness, Elasticsearch service probably is not on the top right because it has an hourly cost, but it's very easy to use. And in this case, we also have a dead letter bucket. So all events that for some syntactic reason is impossible to write into Elasticsearch are automatically written into this dead letter bucket so that you know why you don't lose any data. And then you can use Kibana, your favorite tool, to analyze all the business events of your company. And the event replay, again, on the top, there's your application here that is processing the events. And at the bottom, you have just an SQS queue that can store up to for 14 days your events. And there's a replay function that can be connected to this queue and just will reinsert the event at the top for your application to replay them. And if you tweak a little bit, you can plug them into a different environment if you want. So from production to test and so on. So to make this even easier to understand, we build also a sample application. It's a sample e-commerce application. Here in the front end, we have the command part. You remember we have this command and events. So from the outside, you will receive commands like buy this item, create this order. Then this command is published as a publish and subscribe event, so it becomes an event. And then it's processed at the top by your own custom business model. In this case, we just have a Lambda function that will process the order and insert the order on DynamoDB, but of course, you can do better than that. And then we have the tree pipeline that will store, backup, give you analytics. With analytics, you can also set filters. So for example, I'm only interested to store orders that are bigger than $100 because those is where I want to run my analytics. The small orders, I'm not interested into that. And then you can replay them. So this is completely available as a whole serverless application in the serverless application repo. And if you look at the description of this application, you see that there are 4 nested apps that are the one that I was describing and the e-commerce checkout, so the backend of the application. So if we go back here, this is the main application, and then we have the 3 pipelines and your custom pipeline that is the custom pipeline of this example, and they are all here. Everything here is open source on GitHub, so you can just take them and open issues and ask us to add more features if you're interested, and you can take them and plug it into your application very easily. We can also generate the same syntax to copy and paste if you want. So these are my takeaways. So events are really an important component of serverless applications. They are an immutable series of facts about your business. Think about how you interface. So normally you need a front end that takes commands from your customer, from your user, but then transform everything into an asynchronous event that broadcasts the behavior of your business to whoever is interested. There's an interesting session by Tim Bray, one of our senior principal engineers, that talks about when you create a new service, if you can broadcast the result for everybody to use, you're probably giving a help to yourself in 6 months because you will need to rebuild something that is, and you can just plug in the output of the other service. Events really minimize coupling and increase autonomy because I'm not doing one-to-one communication between a commander and someone that receives the order. I'm just telling you a fact that anybody can use. Think about distributed transactions. That's the hardest part of this kind of architecture, especially with serverless. Sagas and state machines can really help you manage with compensating transaction and reduce the complexity with a logical framework how to solve this problem. And when you build serverless application, think of components. If you see that your serverless application is too big, probably you can decompose it into smaller applications that use one or more function. And if you make them reusable, you can share it inside your AWS account or publicly with everybody if you prefer using the serverless application repository. Thank you.